Our next speaker is Joerg Grosse from OneSpin Solutions. He's a product manager at OneSpin. His title is Rethinking Coverage in a Multi-Verification Tool Environment. Joerg recently joined OneSpin Solutions as a product manager for functional safety. He has more than 20 years experience of EDA, functional verification and ASIC design. As co-founder of a successful Silicon Valley-based startup, he was central in developing the concept of fault/mutation testing into a state-of-the-art EDA tool. He deployed this technology in many leading semiconductor companies, increasing the quality of their functional verification. He holds a diploma in electrical engineering from the University of Applied Science in Anhalt. Joerg.
Thank you, Mark. Short introduction to OneSpin Solutions. OneSpin is a formal verification company, and the products are ranging from static checks to property checking. We also have an equivalency checking tool, and recently we are investing a lot into safety, what we call safety verification, so trying to address safety critical problems in the automotive industry. My talk today is about coverage, and what I would like to touch here is we are a formal verification company. As we heard today, formal methods get adopted more and more. Those formal methods or formal verification, they're going to produce coverage data. And how are we merging, for example, this coverage data with simulation-based coverage data? What are good metrics for this? So let's recap a little bit. What coverage types do we have? So two major types. We have what we call functional coverage. Functional coverage is actually derived from the specification by humans. So it's defined by humans. So it's by nature error prone. It should be traceable back to the requirements. That's important. Examples for functional coverage: for directed test, fast assertion holds, we have our coverage points, and maybe once the portable stimulus working group, the new Accelera group, defines us a nice portable stimulus definition, we might also have a path in the, through a verification graph at some point as a nice functional coverage point. On the other hand, we have what we call structural coverage. Structural coverage is actually derived from the design on the test or from the model by a machine. So from that perspective, it is not specified by humans. So it can't be tricked easily. And with the structural coverage, we actually demonstrate that the functional coverage is complete. And examples for this are code coverage and fault coverage. If we put this into perspective, what we just said, we have our requirements there. We define our functional coverage model, and when we execute the simulations, we will generate a nice report for functional coverage. However, the functional coverage measures, or it doesn't measure, it's implemented with stimulus or constraints, or checkers and assertions. So in terms of when we have a simulation-based environment, we have the stimulus and the checker. When we have a formal environment, we have the constraints and the assertions. So then we're going to measure the structural coverage. And as said, we derive that from looking at the DUT. And in order to measure this side, the stimulus, we have good measures. For example, we have the code coverage. But what gets often discounted is how good are my checkers and assertions. And I believe Steve from Dialog had a comment on that. It doesn't make sense to run zillions of stimulus if you're not checking for the outcome. And last but not least, if we measure the coverage, that also goes into our final report. So going a little bit deeper on the structural coverage method, As said, on this, in the simulation-based environment, we have our code coverage. That's pretty good to measure how good our stimulus is. When it comes down to the checkers, how good is my checking? We have fault coverage or mutation testing. So, for example, the tool for the tool which measures how good the checkers are, for example, certitude. And on the formal side, we have nothing right now, but that will change on the next slide. So, in terms of formal verification, the first thing we need to do is we need to identify constraint locations. And constraint locations are identified by essentially unreachable code locations. And if we have such unreachable code locations, they obviously limit the scope of an assertion. Over-constraining can actually happen quite easily. If you do a typo in your assumptions, you might constrain out important code sections. And when we do our measurements of the constraints, of the constraint location, there shall be actually no constraint locations left when we do our sign-off, or they shall be explained. So we have developed in OneSpin, we have developed a tool called Quantify, which can identify such constraint locations. As you can see here, it highlights the code, which are not considered actually by the assertions because they are constrained. We also identify that code. So we ticked our box here in terms of the constraints. Now let's look at the assertions. So how would we measure the quality of an assertion? Assertions typically have what we see here, a cone of influence. And this cone of influence can be determined pretty easily by just walking down from the inputs of the assertions hierarchically through the design. However, whatever is in this cone of influence of an assertion is not necessarily verified by this assertion. Therefore, what we do, we modify locations inside the source code which are inside this cone of influence of the assertion, and then we expect that assertion to fail. And that would be a proof that that this code location is verified by this assertion. So then when we run our analysis, we end up with, for example, unobserved locations. And unobserved locations point to incomplete verification. So, for example, we could have missing functional coverage elements, wrong implementation of an assertion, so we have a bug in there, so the assertion doesn't do what it's supposed to do. And obviously, if we have unobserved locations, this can also hide design bugs. Like in simulation, this type of analysis provides us with the most advanced and powerful metric, so it leaves no room for interpretation. You can imagine if I inject the bug into the design and the assertion fires, that's very good. If it doesn't, there's no room that I can argue, well, there's something else which would detect it, which would detect this bug. However, like everything which is good, it also has challenges. So if you imagine you have hundreds or thousands of assertions, you have many locations in your design. If you do a primitive analysis, you run each location against each assertion, that would simply explode. So one way out here would be concurrent analysis. I mean, by this I mean concurrent location analysis. So you actually looking at many locations at once per assertion. This is very similar to fault simulation. techniques. You can also think of, to solve the problem, if you pick the right assertion for a given location, then, and the assertion fails, that location can be ticked. So you can speed up that analysis significantly by having heuristics to picking the right assertion and location pairs. And obviously, you should also exclude unobservable locations from the start. So if, for example, a location is not in the cone of influence of an assertion, it's no point to analyze it for this particular assertion. There's another challenge here, which is the instrumentation problem. So when you create your faulty model, you can do it in a way that you create a single location instrumentation. So you change the design, write it out, and prove your assertion against it. Another way to do this is also you can have multiple locations inside your instrumentation and then switch them on demand, but that has the downside of increasing the model size. And another problem with the instrumentation is whenever you create something new, it might have problems. So even without a fault injected, this new instrumentation might have problems, and also standards recommend to not do that, for example, the safety critical standards. And last but not least, there's also an acceptance problem here, because it's additional effort. As soon as you apply something like mutation testing, fault injection, that requires typically machine resources, human resources to set it up, and it's hard to justify this often. And also the designer must be involved in the analysis. So we as OneSpin Solutions, we are still, despite all the challenges, we are committed to the advanced structural coverage. And our tool, Our tool identifies potential design bugs by finding unobserved locations. It also identifies dead code and over-constrained locations. You can see here, for example, the green code lines. They are detected by assertions, so they are observed and therefore exhaustively verified. The red ones show you there are still assertions missing, so these lines can hide potential bugs, as well as the constraint locations, like the brown ones here, that can also hide potential bugs. We are, under the hood, we are leveraging concurrent location analysis techniques to speed up the analysis. And also, we don't need to instrument the RTL code, so we work around that problem by going straight to the model. We also can provide a comprehensive progress metric and generate an HTML report which you can pass to your designers to let them review the results. So in terms of the structural coverage metrics, to summarize this, on the simulation-based side, we have our code coverage and fault coverage and mutation testing. And on the formal side, we provide solution for constraints and assertions. Now the question arises, if I have those results, how do I merge them? And I'm coming to my last slide here. So we have the UCIS standard, and the standard actually provides us with means to merge coverage data from different sources. So, for example, we have our simulation data, we have our formal data. However, if you look into the standard itself, it has a reasonable defined data model. And another good thing about the standard is that that supports XML as an interchange format, so that's the plus points here, but it has huge limitations. For example, from my point of view, it's missing a high-level API. Today it's a very low-level C API, which is probably hard for CAD engineers to program in. So I guess that hinders the adoption of a standard like that. Then the merging aspect is also not well defined. Basically, if you are a coverage source, so you are a provider from coverage data, and you are exporting your data, let's say as an XML, in the XML interchange format, you're still at the mercy of the coverage master, basically, to read your data and merge this into his database. So there's no control or any standard to help you to define that more easy. Another issue with the UCIS is it doesn't have any means for fault coverage. What we would need to do here is use the user-defined bins. And last but not least, it hasn't been really adopted in the industry yet. So there is some support for it, but today it's almost impossible to say I'm exporting data from tool A and read that into tool B. Yes, OneSpin, we are actually committed to the UCIS standard. We would like to see it get more adopted, and also maybe we see another round in the standard to address the shortcomings. We will also, from our tool side, we are committed to do the XML report for the interchangeable format, and we are working with partners to move that standard forward, for example, with MyXTVS. And that brings me to the end of my presentation. Thank you very much.
Thank you, Joerg. We have one question online, Joerg. The question is, you mentioned that safety specs don't recommend the use of instrumented code as it can change design behavior. Can you elaborate on that a little? Because the questioner has heard conflicting opinions on this.
Yeah, I know. It's a discussion on it. When you, for example, when you do a fault simulation on the gate-level netlist, in my opinion, the standard recommends that you do your fault analysis on the very same netlist you are using eventually for your layout. If you imagining morphing this netlist, you are actually going away from the paradigm.
Okay. Okay, thank you. There's no more questions online, I don't think. Any more questions from the audience? Do you have? Yep.
Hi. The question I have is related to your observation coverage story, which I believe is related to fault injection, mutation testing.
Pretty much, yes.
Okay, so I have a concern, which is that if you were to mutate an object in the design and you didn't have a sensible looking cover or an assert, that could fail, but there is a real bug in the design, how would you imagine a fault injection based approach can give you better confidence? Because I've seen designs with tighter constraints with bugs in them, but not necessarily anything in my toolkit to find these. No amount of mutation can find anything if you haven't written anything up front. So how do you propose observation coverage can help us close that gap?
So the underlying theory of mutation testing is not that you are injecting bugs and you finding bugs with it. It's more like if you are able to detect those mutations, you are also able to detect possible design bugs. So what I would expect, if you have a bug in the design which has not been uncovered by the verification environment, be it assertion-based or be it simulation-based, you will see that the mutations will also, you will also find some undetected mutations which might point to a verification weakness, and if you fix that verification weakness, this might expose the bug. Is this answering your question?
Sorry.
What is the goal of coverage? Why do we collect coverage, right? To hunt down bugs. If I have a bug that I cannot actually find by any amount of coverage that a tool offers, you tell me one reason why I should actually use any of the coverage extraction mechanisms if I cannot find these bugs. So is it just a metric to please my manager, or is it a tool to find real problems in the design? Because what the question I was saying was that, yes, there are things in the assertion cover space that could actually fire off in the presence of a fault, and I could find a problem. But there are certain bugs that will not surface. I mean, you could mutate, for example, an adder. Let's say an adder circuit, right? I wrote a property, doesn't formally prove exhaustively that the adder works correctly, and the bug is around the area of rounding and so on, right? You mutate the adder, the assertion fails. So you think, oh, I've got everything covered because, look, my property failed under a mutation. But that bug is still there, and it's kind of undiscovered. This argument applies to simulation as well, as you said. So what do you think we can do in the observation coverage, fault detection, etc., to get on top of these things?
I believe we're diverging already on the definition. I don't think these are bug hunting tools. These are tools to, as I tried to point it out on the very first slide, right? The structural coverage is actually, in my mind, a way to confirm that you have no holes, hopefully no holes. You are never complete, right? But there are hopefully no holes in your functional verification as you derive the functional verification requirements from the specification. So it's actually a way to demonstrate that you did not forget to put a requirement into your test plan. And also to avoid problems like, oh, hold on, I stimulated my design to death, but I don't have any checking going on. Yeah.
Okay, maybe best to take it offline. Okay, thank you. Thanks, Joerg. Thank you very much. Thank you.